Hello, this is question 8 from the winter set of exams from Cambridge International Education. It's paper 1-2 from the year 2019. If you look at the description below, you'll find a link to an image of this question. As you can see, this question is split into two parts, A and B. They're both sequence and series. The top one is going to be an arithmetic sequence and series, and the bottom one's going to be about a geometric sequence and series. Before we jump into the question, let me just remind you of the formulas involved around arithmetic and geometric sequence and series. You will be given these in the Cambridge system. It'll be on a page at the back of your exam, or for example in the Irish exam system you'll be given a booklet with all this in it. But you have an arithmetic sequence and a geometric. Arithmetic is where the terms go up by adding. We add them. Each term is a set amount bigger than the last one. Geometric is when we multiply them by something. Each term is the previous term is multiplied by something. So in this question, 8 part A, they tell us over a 21-day period, an athlete prepares for a marathon by increasing the distance she runs each day by 1.2 kilometers. On the first day, she runs 13 kilometers. So that's given us all the information we actually need to get a arithmetic sequence. And find the distance she runs on the last day of the 21 period. So let's first of all make the sequence, I should say. So the sequence is, on the first day she runs 13 kilometers. On the second day, they tell us each day she runs 1.2 more. So on the second day it's 14.2. On the third day it's 15.4. Now you could just continue this way until you got to the 21st term and you would be done, but I don't think we want to really do that. We can see here that it goes up 1.2 each day. We don't have to see there, they told us this. It goes up 1.2 each day. So we simply use this formula here to get the 21st term. The first term is here, second term. So we simply need T21. And we just read from this formula. A, we know A to be the first term. So A is 13. Plus N is the term we're looking for. N is 21 here, so 21 minus 1. And D is the difference between them. Again, we knew this is 1.2. So 1.2, and we just clean all this up. This is 21 minus 1 is 20. So 13 plus 20 times 1.2. 2 times 1.2 is 2.4 times 10 is 24. So 13 plus 24, which is equal to 37. So that's part A 1. Part A2 continues with the same person. It asks us to find the total distance she runs in this 13 days. So again, we can write that series out the same as here. We just put a plus in. 13 plus 14.2 plus 15.4. And again, we could just write it all out, but it's 21 of them, and they might have asked 100 of them. 1,000,000 of them. It wouldn't matter to our maths, just would have bigger numbers, calculators can handle them, but we don't have all the time to do it. So we just use another formula. We have the series. These formulas can be explained. I haven't done a class at the moment on my channel, but there hopefully will be by the time you're watching this. So, well, sorry, I don't guarantee that. Probably won't be by the time you're watching this if you watch it early, but if you're some future date, it might be there. So we just use this formula here. This gives me S21 will be the first 21 terms added up. So this is just S21 is equal to 21 divided by 2. 2 times 13. I'm just filling in the numbers. 2, A is now 13, plus 21 minus 1, and D is 1.2. So quite similar to the term above here. If you look up how to prove this term, you'll see it mostly comes from this. Let's see, so we clean this up here, we get 10.5, inside we get 26, and we already did this was 24. And that is equal 10.5 multiplied by 50. And that is equal to 525. 525. So that's 525 kilometers. So fair play to her. In 21 days, she ran that much. And on the last day, 37 kilometers. That's I believe a marathon is 42 about. So she's nearly there. And so she should be fairly ready for it. Hopefully, give it a good time. Fair play. Okay, so that's part A. I'll rub this part out and we'll do part B. I'll keep this here because we'll still need the geometric terms. Okay, part B tells us that this is the first three terms of a geometric sequence. Now, the fact that they tell us it's a geometric sequence is very important to us because we need to know what a geometric sequence is. A geometric sequence is where each term is multiplied by something previously. So just an example, we could have 3 multiplied by 2, multiplied by 2, multiplied by 2. Something like that. Or another example might be 16 multiplied by a half. Because what we multiply could make it smaller. We can multiply it by numbers smaller than 1. Multiplied by a half would be 8. Multiplied by a half would be 4. Multiplied by a half. And so on. They both be geometric sequences. Because they're each multiplied by something. And the other thing to notice here is if 6 divides 3, I get 2. 12 divides 6, I get 2. 24 divides 12, I get 2. The ratio on this guy is 2. Again, if I get a common ratio here as well. 8 divided by 16 is a half. 4 divided by 8 is a half. 2 divided by 4 is a half. And that will be true all the way along. If I multiply by the previous term, I get the ratio, the common ratio. But we're not looking at either of these two. We're looking at this one up here. Well, it's just the same. If they tell me we have a geometric sequence, I can just say that the second term divided by the first term must equal OR. That doesn't really help me. But I could also just say the third term divided by the second term equals OR. Again, that doesn't help me. But the fact that OR and OR equal each other does. If I, instead of writing both of these guys out, how about I just write this divided by this is equal that guy divided by this guy. Because it's a common ratio. Just like in the numbers example, and the second divided by the first should be equal to third divided by the second. Should be equal to 20th divided by the 19th. Should always be equal. So we know this to be true because it's a geometric sequence. So I can just solve this. Now I'll go ahead and solve this. Let's multiply both sides by x. I'll get x minus 3. So that's multiplied the left, so the x's cancel. And on the right, I'll get x multiplied by x minus 5. Now let's also multiply both sides by x minus 3. On the right, x minus 3 will cancel with this. And on the left, I'll get another x minus 3. This is just as true as this. Once x does not equal 3 or 0, which, oh, oops, they never told us that one. That's fine. Oh, I guess we could just put an example in 3, 0, and minus 2. That's not a geometric sequence. So I know x is not equal to 3. And again, 0, minus 3, minus 5, that is not a geometric sequence. So I know x is not equal to 0. Or in fact 5, or, well, I'm not sure what's next. Okay, that's just a little bit of housekeeping. I just wanted to make sure what I could divide by these numbers. I probably should have been more careful, but I'll show you another way to do this question, that won't matter. Okay, let's solve this. We multiply this out, we get x squared minus 6x plus 9. Multiply this out, we get x squared minus 5x. Let's take x squared from both sides. They're gone. Let's see. Well, I want x to be a positive usually, so if I add 6 to this side, 6x and 6x, I'll get 9 left there, and this will just become x. There we go. X equals 9. That's our answer. Now, another way you could have done this is you could have used this formula here. We could have said that t1, let me just put it here, t1 equals x, but it also equals a or to the power 0. So equals a. X equals a, basically. T2 would have given us, I'll write this number first. T2 would have given us a or 2 minus 1. And that is also equal x minus 3. But I know what a is. A is I already know a is equal to x. So I can help to solve for or. Still not enough. But then one last one. T3 would equal a or squared, which is equal x minus 5. I won't do it all out because we've already done the answer here. But if you solve all three of these together, basically the first one helps simplify the second one. You get or is equal to x minus 1 divided by x. And then that will help solve the last one. You'll get x multiplied by x minus 1 divided by x squared is equal to x minus 5. It'll be something like this. You'll get an equation like this that you'll have to solve for x, and hopefully you'll find 9 again. Alright, that's B part 1. Okay, part 2 then asks us, find the fourth term in the sequence. So here we have the first, well, let's write what these are here. We have, the first one's 9, x is 9. The second one, 9 minus 3 is 6. The third one, 9 minus 5 is 4. So really what comes next? So you don't have to do any formulas if you don't want to. If you are able to see what comes next, just write it down. But I'll show you, maybe this formula here would be very useful for us. We want T4. T4. The only problem is, I don't know what A is. Oh wait, A is just the first term. So T4 equals 9. Or, I don't know what or is. How do I get or? Oh, well, or is always just the second divided by the first. Or the third divided by the second. Just like just like we said here. Second divided by first. Third divided by second. So let's just use second and first. So that or is just 6 divided by 9. And to the power of n minus 1. N is 4. We decided that number. So 4 minus 1 is 3. That's what T4 is. We just need to do this out. Calculator will do this for us. But let's do it ourselves. 6 divided by 9 is the same as saying 2 divided by 3. Power 3. This is equal to 9. Let's see. 2 cubed is 8. 3 cubed is 27. And let's see, 9 divides into 27 3 times. So we're just left with an 8 and a 3. And you could have seen this at the start, perhaps. Let me write here, 8 over 3. What's changing each time? What's multiplying each of these terms? What multiplies 9 to get 6? 2 divided by 3, that's 2 thirds. 2 thirds of 9 is 6. 2 thirds of 6 is 4. 2 thirds of 4, just multiply by 2 and divide by 3. 8 over 3. Next term is 2 thirds of 8 over 3. 2 times the top is 16. 3 times the bottom is 9. And we can continue on with this sequence once we have the clue. But that's part 2. They just wanted 8 divided by 3, the fourth term in the series. Now, the last part 3, I'm just going to squeeze it in over here because it's very short. It is find the sum to infinity of this progression. So if I add this up forever, I love these. A lot of people in maths love these things, sum to infinity. We're adding forever, something that's impossible. But we're going to get a very simple answer out. So we have 9 plus 6 plus 4. Surely it's just going to stay going up. We're still adding numbers with value onto it. But no, it's not going to add up forever. And we can actually figure that out from this line here. When n is infinity, now they give us a formula for this as well. S infinity is equal to well, let's figure it out here. When n is infinitely big, or to the power of a really big number, it's usually a really big number, except for the fact that or is actually less than 1. Or is 2 thirds. When you get the power of a small number like that, 2 thirds, it's going to get smaller each time. Try it on the calculator. 2 thirds to the power of 2 is 4 ninths. 2 thirds to the power of 20 gets really small. 2 thirds to the power of 100 gets even smaller. This number is just going to become 0. So we're just left with a multiplied by 1 on top. So we're just left with a divided by, and the bottom doesn't change, 1 minus or. So that gives us this infinite, this sum to infinity here. So we can just fill these numbers in. A is 9, which is good because my A looks like a 9. It's 9 divided by 1 minus 2 thirds. 1 take away 2 thirds. Use a calculator if you're not good at fractions. But really, 1 divided by 2 thirds, you're left with 1 third. You have a whole cake, you take 2/3 of the cake away, you're left with 1/3 of the cake. So we're 9 divided by 1 over 3. How many times does 1/3 go into 9? It goes into 1 3 times, and it goes into 9 another 9 times, so 27. Again, use a calculator if you're not quite good with fractions, multiplying, dividing, or adding them. That's the answer though, I find that fascinating. If we add these numbers up forever and ever, and I mean forever, not just the first 100, the first million, the first billion, we will get a solid number, 27, which is pretty fascinating. Okay, I hope you enjoyed that. If you have any questions about sums to infinity, about anything else, if I've made any mistakes, please put them in the comments below. I'll do my best to get back to you. Until then, have a good day.